Look, there is a massive and honestly kind of dangerous gap between what you think your teachers want and what Cambridge examiners actually reward, especially in the IGCSE Physics 0625 syllabus. See, simply describing what a motion graph looks like, that is not going to get you the marks. Examiners aren't looking for just some casual observation, they are hunting for precise scientific command words. So today, we are decoding exactly how to translate complex visual data into those top band answers that secure maximum marks. Let's get into it.
Right, so this is the painful reality of the mark scheme, and it literally costs thousands of students their A-star every single year. A student looks at a motion graph and they write something like, the speed goes up and then down. And it sounds logical. It perfectly describes the visual shape. But this vague, descriptive mistake, it loses crucial marks. Ordinary revision totally fails here, because just reading a textbook doesn't actually train you to use specific command words. The examiner wants to see accelerates to terminal velocity followed by high deceleration. That tiny shift in vocabulary, that's the difference between just passing and totally excelling.
So let's grab an easy win right off the bat by breaking down the absolute fundamentals of motion graphs. You absolutely must instantly distinguish between a distance time graph and a speed time graph. Okay, for a distance time graph, the gradient equals speed, and a horizontal line just means the object is stationary. Simple enough, right? But drop down to the speed time graph. Here, the gradient is equal to acceleration. A downward slope means decelerating. A horizontal line means constant speed, and crucially, this is a big one. The area under the graph equals the distance traveled. Memorizing this exact distinction is your very first line of defense against dropping super easy marks. Now, understanding those basics is great, but applying them to complex curves, yeah, that's where students tend to panic. Now, in just a minute, I'm going to show you the exact examiner clue that completely changes how you read negative relationships on these things. It's a real game changer. But first, you really need the framework that actually makes that clue obvious. Because without this framework, you're honestly just guessing at what the graph means. Okay, here is the core 4-step framework that transforms just a basic understanding into a top band Cambridge mark. Step 1, concept identification. Ask yourself, what physical law are we actually looking at here? Step 2, evidence extraction. You need to pull specific points or values directly from the curve. Don't be vague. Step 3, scientific reasoning. Connect that extracted data right back to the physics concept. And finally, Step 4, examiner-safe wording. This means swapping out everyday phrases like speeding up for accelerating. If you apply this relentlessly, your answers become absolutely bulletproof. Let's actually look at this framework in action. This is the classic Cambridge parachutist case study. It's a favorite for a reason. Real-world physics is rarely just a straight line, right? So interpreting a curved graph like this helps us decode really complex relationships. What we have is the speed of a parachutist plotted against time during a free fall. By extracting data from the changing shape of this curve, specifically looking at the gradient, we can accurately describe the physical behavior of the fall. Let's break this down chronologically, step by step.
Focusing on the first phase, right at point A, the parachutist jumps. Her speed increases, meaning she accelerates, and notice that really steep, aggressive gradient right at the start. Just past that, speed is still increasing, but a bit more slowly, which means acceleration is dropping. Then, bam, we hit point C. The speed reaches its maximum value and just flattens out until point D. This is that critical concept of terminal velocity. A flat gradient on this graph, that means zero acceleration. But right at point D, she pulls her parachute. That sudden, steep downward slope represents an immediate super high deceleration.
Now watch what happens next. At point E, the curve flattens out slightly. The speed is still decreasing, sure, but the deceleration is lower now. By point F, the parachutist establishes a brand new, much lower constant speed, basically a safer terminal velocity to approach the ground, returning acceleration back to zero. Finally, at point G, she lands. The graph drops sharply to the x-axis, coming to a complete stop with a massive deceleration. By stepping through points A to G using strictly examiner-safe terms, we've perfectly mapped out a highly complex physical event. All right, I want to pause for a second and test your command of this material. The crucial question is, where exactly on this graph is a negative relationship shown? Take a mental pause right now. Literally predict the answer before I reveal it. Think about the curve. Where do you see a negative relationship, and what does it actually physically mean for our parachutist? Okay, let's see if you nailed it. A negative relationship is defined by a downward sloping line. Basically, as the values on the x-axis, which is time, increase, the values on the y-axis, our speed, fall.
On this specific graph, this happens exactly from point D through E down to F, and then again from G onwards. Physically speaking, these are the periods of deceleration. Nailing this exact terminology is the specific clue the examiner is just waiting for to award you full marks. But look, even with perfect descriptions, students still fall into massive traps. Let's do a quick spot the error check. Imagine a student writes, the area under a distance time graph shows speed. Okay, here is your strict examiner-style correction. That is entirely incorrect. As we established earlier, the gradient of a distance time graph is speed. The area under a speed time graph is distance traveled. Mixing these two up, it is one of the most common and honestly most devastating errors in the 0625 exam. You've got to keep them strictly separated in your mind. So you now have the exact framework to perfectly describe complex motion graphs. You can track terminal velocity, you can spot negative relationships. Awesome. But what about the calculation traps? See, the 0625 syllabus doesn't just want you to describe this graph. It absolutely demands you calculate the acceleration when the change in speed is greatest, or determine exactly how many seconds she traveled at 5 meters per second. Stopping your revision right here leaves you completely exposed to the brutal calculation traps waiting in your next paper. Decoding the examiner language for those specific calculations, that is your mandatory next step to secure top marks. We're going to break down exactly how to extract the data for those math skills in our next explainer. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Because think about it, if a simple description mistake just cost you 3 marks, imagine what a completely botched calculation will do to your final grade. Get over to the next explainer and let's lock those calculation marks down. I'll see you there.